Hi everybody, I hope this video finds you well. In today's video, which is going to be a pretty short one, we're going to be finishing up section 6.1, which was your introduction into linear transformations. In this video, what we're going to do is we're going to focus our attention on linear transformations from Rn to Rm and see that these transformations can be completely described via matrix multiplication. So this will be a quick video, but its main focus will just be on linear transformations from Rn into Rm. So let's start with this quick theorem here. So let's let A be an m by n matrix. Then the mapping that goes from Rn into Rm defined as where you take the transformation of a vector and you define it as that matrix multiplied with that vector. Then that mapping is guaranteed to be a linear transformation. Now, first of all, let's make sure we understand why this goes from Rn to Rm. If you let X be in Rm, and you let A be an m by n matrix, and what you are effectively doing, right, is you're taking your m by n matrix, and then you're going to be multiplying it by something in n by 1, and that is, of course, going to result in something that is m by 1. So that makes sense about why it goes from Rn into Rm. That's what this transformation really does. So we need to show that it's a linear transformation in general. In other words, what you can really think this theorem is sort of telling you is that if you define a transformation that is based on matrix multiplication, it is always going to be a linear transformation. So to prove that, we've got two things that we need to do. We first need to show that if we take t of x plus y, that is going to be t of x plus t of y. In other words, first thing to show is that you can distribute your linear transformation over vector addition. So let's go ahead and do that. T of x plus y, well, according to that, that's going to be left matrix multiplication by this matrix A. So it'd be A times x plus y. And of course, we know that matrix multiplication certainly distributes over vector addition. So this is ax plus ay, which is t of x. That's the definition of what t of x would do. And that is t of y. So we're all good. So that shows that our transformation distributes over vector addition. Now we need to do the same thing for scalar multiplication. So we need to show that t of kx equals kt of x. So t of kx, right, that would be a times kx. And then, of course, this is a matrix, this is a scalar, and this is a vector. This k here can be placed anywhere, so we can just pop it out front. So this is kax, and that's, of course, ka times x. And, of course, this guy right here, well, that is the definition of the transformation. So this is k times t of x, check. So t from Rn into Rm, t of x equals a times x is a linear transformation. So this is not a super deep theorem. All this is basically saying is if you define a transformation from Rn into Rm by left multiplication by a matrix, then it is guaranteed to be a linear transformation. What's actually interesting, though, is that actually every transformation from Rn to Rm can be thought about as a matrix multiplication. This theorem tells us that every matrix multiplication is guaranteed to be a linear transformation, but the opposite is true too. Every transformation from Rn to Rm can be thought about as a matrix multiplication. So let's see how to talk about that. So as a definition here, let's let t be from Rn to Rm, and that's going to be a linear transformation. So if we know that we have a linear transformation from Rn to Rm, then we can actually figure out the correct matrix where matrix multiplication would correspond to that linear transformation. What we do is we take A and we define it to have the columns that are this transformation applied to each of the elementary column vectors. Remember, these elementary column vectors, E1 would be 1 and then all zeros, E2 would be 0, 1, and then all zeros, and En would be all zeros until a 1 in the last position. So if you apply your transformation to every one of those elementary column vectors and you use those as the columns, then that matrix that you create is called the matrix of T. And the big idea here, the whole point of this sort of little extra video attached to section 6.1 is that T is equivalent to matrix multiplication by A. In other words, what we are saying is that every transformation from Rn into Rm can be described or viewed as matrix multiplication by a particular matrix, and now this tells us how to find those matrices. Now, we could go through and do a proof of that. It's not a particularly bad proof. It is sort of done in your textbook, but I think you guys can just read through and take a look at that. Instead, what I'd like to do is just take a look at a quick example to sort of show you guys that any transformation we can talk about from Rn into Rm can be described via matrix multiplication, which really tells you guys why all of the stuff that we're sort of talking about sort of connects together. Yes, we learned about matrix multiplication as just an operation on matrices, but it also turns out to completely describe this type of linear transformation. All right, so as this example, let's consider this linear transformation that goes from R4 into R2, defined by when you take something in R4, x1, x2, x3, x4, you treat it as x1 plus x4 and then x2 minus x3. What we're going to do is we're going to use this definition to determine the matrix of T, and then use this matrix of T to determine T of 1, 2, 3, 4. Now, before we do all that, let's just make a note that we should be able to very easily just look at this definition and know what T of 1, 2, 3, 4 is. Well, what do? Well, it's apparently when you do T of 1, 2, 3, 4, you add the first and last components, and then you subtract the middle components. So this should work out as if we add 1 and 4, we should get 5 as our first component, and if we subtract the middle components, 2 minus 3, we should get minus 1. So once we've determined the matrix of T and we use matrix multiplication onto 1, 2, 3, 4 as a column vector, we should get 5 minus 1. So let's go ahead and see that. Okay, so in terms of this matrix here, what we're going to have to do is we're going to have to figure out what the transformation does to E1, E2, E3, and E4. Why do I know that we need to do it for all of those? Well, I have to do it for every elementary column vector from the domain. So E1, E2, E3, E4, since it's going to be a dimension 4 sort of domain here. So let's see what that would look like. So E1, well, that's just 1, 0, 0, 0. So what happens when we plug that in here? Well, that's going to be 1 plus 0 and then 1 plus 0 and then 0 minus 0. So it looks like the first thing that would come out is just 1, 0. And notice that when we do this, we treat everything as column vectors here. Right? Again, column, row vector doesn't really matter when you're talking about R4 and R2. It's just two different ways of writing the same thing. For E2, then that would be 0 plus 0, 0 plus 0, and then 1 minus 0. So that sounds like it's going to come out as 0, 1. For E3, right, that would be 0, 0, 1, 0. So that would be 0 plus 0 and then 0 minus 1. So it sounds like 0 minus 1. And then finally for E4, that would be 0, 0, 0, 1. So 0 plus 1, 0 minus 0. That comes out as 1, 0. So there is our matrix that represents this transformation. In other words, what we're really saying is that you can define this transformation like this, that's sort of in like, almost like what you guys are used to from function notation. It says put in this, get out this. Or you can define it as left matrix multiplication by this matrix. Now let's confirm that matrix multiplication by this matrix really does give us the same result in the one that we calculated. So let's see. If we take, as a sort of check here, if we take 1, 0, 0, 1, 0, minus 1, 1, 0, and we multiply by this guy as our input and treating it again as a column vector, 1, 2, 3, 4, let's see what we end up getting here. So we take this row times this column. That's going to be 1 and then 0 and 0 and 4. 1 and 4, that's going to give us 5. And then this row times this column, that's going to be 0, 2, negative 3, 0. 2 and negative 3 is going to give us negative 1. What do we notice as the result here? 5, negative 1, exactly the same as 5, negative 1. Check. So this shows you guys that this transformation, totally fine to define it like this, but you can equivalently define it as a matrix multiplication. That's actually it for what we want to say about section 6.1. This little video here is basically just to sort of reveal you guys this sort of deep fact underneath about transformations from Rn into Rm. And we're basically saying that every transformation from one Rn to a different Rm or even to the same one has to be equivalent to matrix multiplication. Now, it turns out you can even generalize this further, and there is, if we were going to go into a deeper discussion, it turns out that every transformation from any finite dimensional vector space into another finite dimensional vector space with a given basis in each space can be defined as a matrix multiplication. That's a little beyond the scope of our class, so we're just going to talk about it in terms of Rn and Rm. In the next video, we'll be skipping section 6.2, which actually does go into that discussion a little bit further. But instead, we'll be moving into section 6.3, which talks about some properties of linear transformations, particularly what is called the sort of kernel and range of a transformation.